Yes, thank you. Mic works, excellent. So, as I said, the title of my talk is JupyterHub as an interactive supercomputing gateway. We're talking about interactive HPC with BatchSpawner, profile, single sign-on, and more. My name is Michael Milligan. I'm the head of application development at the Minnesota Supercomputing Institute. We're essentially the research computing arm of the University of Minnesota. And we've recently started a significant push for interactive HPC as a service that we support at the level of one of our first-class services. So traditionally, as was mentioned in the keynote, HPC has been a field where you get work done by SSHing in and then doing some stuff at a console. We are gradually expanding that field. Our institute was an early one to jump on the idea that providing remote desktop access is a very user-friendly thing to do. So we've had remote desktops for some time, and people use those heavily, even if all they're doing is opening a few terminals and doing things at the terminal. We're now moving into the realm of web services, and interactive HPC through web services is kind of a new frontier for us. So partly, the reason we jumped on this interactive HPC idea is thanks to you Python folks. IPython Notebooks, IPython Parallel. I kept doing these cool demos using these tools, and people said, hey, you know, this is great stuff. We should consider supporting it more widely. Unfortunately, the user experience wasn't great because of the number of things we had to teach our users. There were a number of hoops you have to jump through. You have to set up a remote desktop because in our networking model, there was no reasonable way to run the browser on your own computer. And that meant that you have to craft and submit your own job scripts to suitably start up your Python notebook. And in addition, because your remote desktop isn't actually running on the supercomputing cluster itself, that meant we had to teach our users how to use SSH to set up networking tunnels to get their browser through to their job and get the traffic back, and it was seriously half of the slides in my tutorials. So we started asking the question, if only there was a way to just run this as a service, we could set all this up once, provide our users a URL that they can visit, and everyone would be happy. We could cut my tutorials in half, and I go get a longer lunch. So along comes JupyterHub. JupyterHub's been in circulation for a couple years now, I think. I've blatantly stolen the How It Works graphic from Jess Hammack's talk last year to illustrate some of the concepts. The architecture of JupyterHub, for anyone who's not familiar, you have a configurable proxy sitting at the front, and that's what users are actually connecting to. And that configurable proxy is going to forward their traffic to various places. It either forwards it to a hub service that does the work of coordinating the various modules, including the authenticator that determines who the user is, the spawner that starts up the user's notebook server, or the configurable proxy can send their traffic directly on to a notebook server that's running on behalf of that user, which in the traditional model is running in the same place as your hub, or is maybe running in a Docker container somewhere. In our model, these notebook servers need to be running on a node in a supercomputer in response to a job that user has submitted. So I'm not sure exactly when this revelation came, but I think it was when someone mentioned the configurable proxy that got the ball rolling. So I chewed on this for a while. And eventually came up with something that we've called the BatchSpawner. This started out as a hack on something called the Slurm spawner by Michael Gilbert. And I took liberal inspiration from a blog post that Andrea Zonka wrote relating to their work deploying Jupyter at SDSC. We came up with something called BatchSpawner that was essentially a generalization of those approaches. So I figured the do the simplest possible thing that could work thing has already been done. So I attempted to do the most general thing that could possibly work. And we've produced a system that very robustly generates templates for job scripts, parses output from scheduling systems, and does it all using configurable traits, which means it's highly overwritable. As a result, that's the entire code, minus with the comments stripped out for brevity, for the spawner that launches jobs if you are on a supercomputer using the torque scheduler. I snipped a few lines out of the batch script template, but this is the sort of thing that a site administrator can then write once and deploy, and essentially not have to care about it anymore after that. If you add more features, you can go in and add them in your job script, but your user essentially gets a pre-canned experience. Here is your Jupyter experience. Here's your notebook. It's all set up. The configurable proxy is going to take care of the work of doing all the tunneling for you. And from that point, we already had essentially a working product. So at this point, we also have spawner support for the Slurm scheduler, for the Sun Grid engine, which is now Univ someone or other. And those have actually been contributed to the GitHub page. So we already have people who are working with this and developing it. And this has been deployed at my last count, 7 or 8 institutions. So I'm actually not going to stop here, because there's more to talk about. So the next question we asked ourselves is, OK, we've got this batch spawner capability. We've got the ability to start Jupyter Notebooks on behalf of our users and do sort of all this fiddly plumbing for them. But now we confront the fact that, well, we have more than one cluster. We have multiple queues that expose different functionalities, different types of nodes you might want to use. Maybe you want a high memory node. Maybe you want a node with GPUs. Is there an easier way to expose all this rather than just setting up a JupyterHub for every possible configuration? And the reason that this isn't immediately trivial is that JupyterHub itself, the hub code doesn't have, by default, any way to configure spawner creation before the spawner is actually created. It has recently gained a functionality to present a form to the user during the process where it's going through the requests back and forth with the user to start up their notebook. But to use this form, there's no specification about what data it contains. The spawner would have to know to go look at this form, and that's fine for a spawner I write. I could totally have written BatchSpawner to just do that. But then what if someone wants to go plug in the Docker spawner? Then they'd have to go and modify the Docker spawner, and I'd have to get them to agree to use the same metadata format, and that sounded like kind of a mess when the solution has actually already been provided. So we realized that everything JupyterHub is written using traits, and traits are easy to override, either from configuration files or at class creation time, which means we can actually inject data at runtime. So we decided to write essentially a wrapper spawner that takes information that the user provides and emulates the public API of a spawner. So it doesn't instantiate a spawner right away. Instead, when a user connects, they're talking to the wrapper spawner, and the wrapper spawner just tells the rest of the JupyterHub infrastructure, hi, I'm a spawner. Don't ask any questions about me because there's nothing here. And then the user gets prompted with a form. And what goes in that form? Not actually specified yet. But supposing that you can populate the state, then the wrapper spawner will go and choose the appropriate class to start up your notebook with. It'll go and populate your class with whatever parameters you've chosen. And it does it all at runtime, not at configure time when the site administrator is installing things. And then goes and proxies all those calls through to the real spawner you've created, which I have to admit is a pretty cute trick, but not inherently useful until we add the concept of profiles. So by adding a concept of profiles, we can now intervene at the point when a user is starting up their notebook and ask them a question that becomes meaningful. In our chosen implementation, we allow the site administrator to create a list of profiles, and it'll then go and auto-generate some HTML from that list and populate it into the form that the user gets prompted with. And the user can then choose from the different profiles that we've chosen to define. In this case, we have one supercomputing cluster called Masabi, another one called the interactive cluster. We've got different job types. And when the user selects one of those, it's just going to send a keyword back to the hub telling the spawner, oh, the user wants this profile. And it goes back to the configuration that the site administrator has defined and picks all the various traits out. And you'll notice that I'm not even restricted to using a single type of spawner for these jobs. In this example configuration, you can, depending on the profile the user selects, either run a notebook locally, which we do not support at MSI, but you could. Or you can run on a supercomputing cluster. You can just change a few variables to change which cluster you're submitting to, what technology it uses to run jobs, and essentially any other aspect of that cluster. And I found this particularly nifty. Because this selection is saved as user state, all of your users can be using completely different technologies to run their Jupyter notebooks. Any combination that the site administrator has decided to support just works transparently. So we were really excited to get this working. And I would just note that the wrap spawner and profile spawner that implement this are included in the BatchSpawner GitHub repo that I linked to earlier. So another question that came up repeatedly is, how do you do authentication? It's possible to just password protect a notebook, but that hardly scales. There are, in addition, various plugins for JupyterHub that do authentication in various ways. The simplest one being, you can do an LDAP query and have your user type in their username and password. But at a site like ours, it's a bit deprecated to have a public-facing web app that just takes usernames and passwords. You can do it, but they'd really prefer that we do something more modern. For security, we conceivably might also not even have real users on the web server that's running this hub. We might decide that it just has some very basic configuration, possibly a stripped-down Docker container that doesn't have users in it, because all of the user-relevant stuff is going to be running somewhere else over in our supercomputing cluster. So possibly you're going to have a server that only knows how to talk to your job scheduler. So the solution to that, in our case, is to recognize that at the University of Minnesota, we have a shibboleth provider. We've got some local wrappers that provide a web SSO system. This is all already in place. And as a result, we already have Apache configurations that you can just dump onto a server that will interface Apache to your existing authentication system. So it's really easy to do that, whereas it's relatively difficult and error-prone to go and write my own endpoint in Python or some other language to do all that again. That's extra work I don't want to do. So the result there actually turned out to be quite simple. There's a authenticator module called Remote Spawner that is literally about 20 lines of code that consists entirely of pulling some headers out of the request that Apache proxies through. And then Apache can do all the work of figuring out our authentication, which could be they logged into the university's central authentication provider, or it could be they used the university-provided two-factor tokens, or it could be they used the two-factor authentication app on their phone. And I don't have to care in the slightest. I just get a username from Apache that I can trust, and I plug it into the configuration, and it's off to the races. Now, the one downside to doing this is you're adding another reverse proxy in front of your setup. And there's been a good deal of back and forth on the JupyterHub GitHub issues figuring out exactly how to do this. It's a little bit arcane, but at least for Apache, this is the recipe that has worked for us. And the reason it's arcane is mainly just that the URLs, there are various requests that the user's browser can make. They might be regular HTTP requests, or they could be WebSockets. And you actually need to separate those out because they get proxied separately. So that's authentication. The next important point, because this is meant to be a production service, is deployment and testing. So the MSI is a CentOS 6 shop. That's old, but the physicists in the room will sympathize. At least it's not scientific Linux. And we use Puppet for configuration management, which means no Docker containers. VMs are usable, but you have to file a ticket and wait a week for them to be created. But we were able to actually encapsulate everything we needed as essentially just Puppet configuration stanzas. In particular, the JupyterHub install is modeled as a directory that contains a Python virtual environment, as well as a node npm module tree. And that directory is, with a configurable path. You can erase it and create it again, so it's completely reproducible. And then separately, you have classes which by virtue of being Puppet classes, the semantics there, for those who aren't familiar with Puppet, is that a class is instantiated on a node, and if you've defined that class on a node, it's mandatory that it succeed, otherwise it will throw an error and tell you a node couldn't be configured. So you find out right away if it didn't work. And the class has to be unique on a node. You can't have more than one instance with different configuration, meaning that it's possible to atomically and consistently configure a given node to serve up a given install of JupyterHub and make sure it started in the init scripts, make sure Apache is pointed to the same one you just installed. And because this is a production service, having a reproducible and testable environment is mandatory. So by pulling in code fresh each time, we're ensuring that we're deploying a clean environment. We tag which commit we want, so we should get an identical environment each time until we change the tagged commit. And as a result, we can easily create a test server just by throwing these classes on a new VM, or a parallel test install by instantiating our install directory on a new path, and get a guaranteed consistent state. One thing we would definitely still like to do would be to hook into the continuous integration framework that JupyterHub is already using for their testing, so then we could get CI testing as part of our development for BatchSpawner and friends as well. We're not quite there yet. Monitoring. Monitoring is another thing that we care very much about. We want to know who's using the system, both for our own curiosity and user outreach, as well as for security. So at our installation, we are monitoring everything with Splunk. So anything at our site that writes anything to a syslog file, that logging output is going to wind up in our Splunk database. So this is nice because the hub and proxy actually generate really thorough logging output. So we just direct their logging output directly to syslog. And then Splunk can digest it all from there and run various saved searches, nightly, weekly, hourly, whatever you want. So for example, I get a nightly email that gives me a table of users from that day, runtimes, failures, what types of jobs they are running. You can see the poor JJ got unlucky that day, but most everyone else's jobs ran. Most of the failures that we see are simply due to that queue being busy. JupyterHub requires that you specify a timeout after which it'll give up. Since this is meant to be an interactive service, We don't want to keep users waiting drastically long anyway. It's not terribly useful if a user goes to start their interactive service and 45 minutes later gets an email saying, oh, your job has started. That's not interactive. So we would rather tell them right away, okay, it's busy right now, you're not going to get this interactive session you asked for, maybe try a different job type. So that's what most of those failures are, is their job didn't start in a few minutes and they got kicked out. The JupyterHub hub itself actually has a really nice dashboard as well, which is a handy way to see at a glance who's using the site. And just by looking at that every so often, I can see that since we announced this in May to our users mailing list, we've got 5 to 10 regular users and about 50 who have used it at some point since then. So I'm counting that as a pretty good adoption curve compared to other things we've rolled out. So finally, next steps. We are aiming to build an all-purpose interactive supercomputing hub. So there's some additional things that we want to do in order to get there. Software integration is important. We have a lot of software at MSI, something like 300 software packages are supported. We'd like to support more kernels. Right now we just have the big 3, Python 2, Python 3, and R. We'd like to automatically do kernel setup when we install software modules. I'm looking at you, R, because building the IR kernel is a bit tricky if you're not doing it in the most default way possible. User handholding would be nice. We'd like to better understand how to do things like auto-populate user configurations as appropriate to the system. So if they are logging into one cluster, we can automatically configure for them appropriate paths and environment variables that will make their life a little bit nicer using that system. Similarly, environment management. We use something called the environment modules system that really sort of assumes that you're using a shell. If someone wants to go and run Mathematica, they type module load Mathematica, and it loads up some environment modules to put things in their path, to put things in their library path. And you fundamentally can't do that in an IPython notebook. So we have to find other ways to do that. Additionally, IPy Parallel. It's been split out. It used to be IPython Parallel, but now it's its own project, which is exciting. It's coming along rapidly, and we like what we're seeing. But it's created some minor complications. It used to have really nice integration with the IPython notebook console. The Jupyter dashboard that has replaced that requires you to enable an extension. And so another thing we'd like to understand better is how do you go and enable an extension for all users as me, the site administrator, rather than having to teach every user to type the Jupyter NB extension enable command. And there's similar minor configuration issues there. Another feature that we're very much looking forward to in JupyterHub itself is support for multiple spawners per user. Right now we have to make a user decide, do you want the interactive cluster or this Masabi cluster or this node with the GPU? And we're always asking what other interesting things can we tunnel through the proxy. Right now, especially for the visualization, there's a lot of interest in something like GPU-accelerated visualization, maybe a no-VNC style remote desktop to integrate with the notebook, which is ironically sort of a call back to our roots. So thank you all for attending. Great audience here. Just as a reminder, got the BatchSpawner repo there. We're the Minnesota Supercomputing Institute. There's our URL. And there's my email if anyone wants to send me questions, or I'm Milligan on the SciPy Slack. Okay, he's telling me I have 5 minutes for questions. So. Way over there, yes.
So I noticed the inspiration for the BatchSpawner was the Docker spawner, but currently does the BatchSpawner actually run each instance in a separate Docker container, or is that something that's planned?
Okay, so the question was, the inspiration for some of these spawners was originally the Docker spawner, which creates a Docker container for your notebook. Does the BatchSpawner run your instance in a Docker container? And the answer is no. As I mentioned, actually, one thing we had to get around is that at MSI, we don't support Docker containers yet because our platform is a bit antiquated for certain technologies. So we are, in fact, running your Jupyter Notebook as part of our ordinary operating system install. It's, we have a Python 3 install that operates just like any of our other software modules. So as part of the job script that gets submitted, we load up that software module and run your notebook from there. But there's no containerization happening, which has the nice side effect that you have direct file system access to our high-performance file system. So most people store all their data in a common file system, and they can just directly access that from their notebooks. More questions? Yes? What would it take to support additional kernels beyond the big three? Not much if you have complete control over the site. The main issue for us is that any kernels we build, they have to fit into our software modules infrastructure. And many of the lesser used kernels assume essentially full control of the machine. They assume you're running in a Docker container or on your own laptop. And so the build process isn't as configurable as we would like, or we just don't understand the build process as well as we would need to get those kernels built and installed in a way that abstracts them off into a software module that we can then invoke and run on our supercomputing clusters. Yeah. Okay, I don't see any more hands. Thank you.